In this video, we're going to talk about the idea of the limiting reactant. The limiting reactant is a concept that addresses the question, when does a chemical reaction stop? We have an example reaction here between magnesium and oxygen gas to make the compound magnesium oxide. If you take a magnesium strip and you burn it in a Bunsen burner, the magnesium strip will burn and create magnesium oxide powder. Now, the magnesium strip is presumably fairly small. The oxygen would come from the air, and the question is, when does this reaction stop? Well, if you burn it in a typical room, the reaction is going to stop when all of the magnesium strip is gone. And when the reaction is done, all the magnesium will be gone, will be converted into magnesium oxide, but there will still be oxygen in the room. In a situation like this, we say that the magnesium is limiting in this reaction. In other words, the amount of product produced is controlled by the amount of magnesium we started with. So if we had a little bit less oxygen, a little bit more oxygen, it wouldn't really matter in terms of how much magnesium oxide powder we'd produce. So, in general, the limiting reactant is the reactant that's completely consumed when the reaction stops. And it's that reactant, that will control the amount of product that you produce in the reaction. The other reactant, in this case the oxygen, we would say that that reactant was present in excess. In other words, we have more oxygen than we actually needed to do the reaction. Now, if I was going to do a calculation involving how much magnesium oxide I would produce, I would obviously start with the amount of magnesium used. I would probably ignore the oxygen here because I'm fairly safe in assuming that a typical room will have a lot more oxygen than the strip of magnesium could possibly use. So I would start with the amount of magnesium, and I would calculate the amount of magnesium oxide based on the magnesium. When you do a chemical calculation where a limiting reactant is involved, the limiting reactant is going to control the amount of product produced. Sometimes it's obvious what reactant in a set of reactants is limiting. So as in this case with the magnesium strip burned in air. Other times it's not quite so obvious. So we need to talk about how do we figure out which reactant is limiting if it's not immediately obvious from the situation. Now, there are several ways you can go about doing this, but the easiest way I think to do it is just to do a calculation. So let's illustrate this with a problem. We have a situation here where we'd like to make some of the compound calcium carbide, CaC2. And to make that, we can make it from calcium oxide and carbon. Let's say we look in our stockroom and we found that we have 100 grams of each one of those two compounds. And the question is, well, using 100 grams of each reactant, how much of the calcium carbide would I actually make? And the issue is, one of those will most likely run out first, but it's not immediately obvious which one. We could say, well, we have 100 grams of each one, but the calcium oxide is heavier, so it has a formula weight of 56.08 as opposed to 12.01 for the carbon. So maybe it runs out first because there's less moles of it. The other side of the coin is we use 3 times as much carbon as we use calcium oxide. So we have more moles of carbon, but it's used at a faster rate. So which runs out first? Well, we may not know. But we can settle this once and for all by doing a calculation. And what we'll do is we will calculate the amount of calcium carbide that could be produced from both of the reactants. And then we'll be able to pick which one actually is limiting. So let's start with the calcium oxide. And we've done these calculations before, so we know the general steps. The first thing we'll need to do is we'll need to convert the grams of calcium oxide to moles using the formula weight of calcium oxide, 56.08 grams per mole. In the second step, we'll need to convert moles of calcium oxide to moles of calcium carbide. In this equation, for every mole of calcium oxide, there's a mole of calcium carbide. And finally, to get the mass, we'll need to use the formula weight of calcium carbide to convert moles to mass. 64.10 grams of calcium carbide per mole. Setting up the calculation, we start with 100 grams of calcium oxide, times sign, draw a line. For the first step, I want to get rid of grams of calcium oxide, so use that factor, 56.08 grams of calcium oxide on the bottom, what it equals to moles of calcium oxide on the top. That gets rid of grams and leaves you with moles. Second step, the part that has moles of calcium oxide on the bottom, on the top goes the other half of that factor, moles of calcium carbide. That leaves me with moles of calcium carbide. So for the final factor, put the part with the matching unit on the bottom, moles of calcium carbide, what it's equal to, 64.10 grams of calcium carbide on the top. That's all three of my steps. So I will go to the calculator, type them in. 100 divided by 56.08. There's actually nothing to enter for the second step. Times 64.10, and that gives me 114 grams of calcium carbide. Now, the issue is we don't know if that's the answer. That is the amount of calcium carbide you would make if all the calcium oxide gets consumed. To figure out if that's actually true, let's do the same calculation but for the carbon. So, starting off, this calculation works much like the other one. We'll need the formula weight of carbon this time. 12.01 grams of carbon per mole. We'll need the ratio for carbon. 3 moles carbon for every mole of calcium carbide. And then the last factor is identical for this one. We're still doing calcium carbide's formula weight, 64.10 grams per mole. Since we had the same amount of carbon here, start off with 100 grams again. Times sign, draw a line. For the first step, I'm trying to get rid of grams of carbon, so 12.01 grams of carbon on the bottom, moles of carbon on the top. That leaves me with moles of carbon as my unit. So my second step, put the mole of carbon part on the bottom, 3 moles of carbon. It's equivalent to a mole of calcium carbide. That cancels out carbon, leaves me with calcium carbide. For the final step, I'm trying to get rid of moles of calcium carbide, so moles calcium carbide on the bottom, what it's equal to, 64.1 grams of calcium carbide on the top. This one went pretty fast because it's almost identical to the calculation up there in green. So let's see what this number actually is. 100 divided by 12.01, also divided by 3. Well, I can't forget that 3 on the bottom there. Times 64.10. And I get 177 grams of calcium carbide. So in other words, if I had used all of the moles, all the grams rather, of carbon, then I should be able to make 177 grams of calcium carbide. The thing is, these reactants don't react separately, so we don't get the correct answer by adding these two answers together. What we have to do is remember that they're reacting at the same time. So you start the reaction with 100 grams of each reactant. After a while, you've made some calcium carbide. Let's say 25 grams of calcium carbide. The reaction's still going. After a little while later, you've made 100 grams of calcium carbide, and then 110, and then 112, 113, 114. And when you reach 114 grams of calcium carbide, then at that point, you literally don't have any more of the calcium oxide to react. So the reaction has to stop there. All the calcium oxide is gone. So it turns out the correct answer is 114 grams of calcium carbide. That's a smaller amount than 177 grams that would have been produced if all the carbon had been used. So, in other words, this reaction should produce 114 grams of calcium carbide. At this point, all of the calcium oxide is gone, and the reaction will stop. If we want to, we can say that calcium oxide is limiting and carbon is present in excess. So it turns out the number we calculated first was the right answer, but we didn't know it until we got the answer for the carbon for comparison. So if you're trying to figure out which of two reactants is limiting, you can calculate the amount of product that can be produced from both, and then just take the smaller number. That will be the actual amount of product produced. Now, how can you tell when you have a limiting reactant situation? Here's how you tell. You will have more than one amount for reactant specified. So if you have a reaction that goes A plus B goes to C, it will say something like you have 25 grams of A and 50 grams of B. How much C can you make? So in this case, we had calcium oxide specified. And also, we had carbon specified. So we had two amounts for two different reactants. Now, you don't have to have the same amount of each reactant. We could have specified we had 100 grams of calcium oxide and 75 grams of carbon, and we'd have worked the problem the same way. But the key is more than one reactant is specified. If only one reactant is specified, like in the problems we've worked previously, then it's not a limiting reactant situation. You just assume all the other reactants are present in excess. So it's limiting reactant when more than one reactant is specified. Now, that's it for this video. Thanks for watching.